So I want to start actually just by acknowledging my own group, and especially Anna and Mariona, who have done most of the work that I'll be talking about today. I should also mention that there's a couple of group members, James and Marco, who are actually here at JQI this week as well. So at some level, this is going to be a talk about atoms and photons. And I think we all know that atoms have been one of the playgrounds for a long time for exploring quantum mechanics, especially in their interactions with light. So the kind of simple story of an atom is it's more or less a two-level system. So it has some electronic structure, but the levels are completely anharmonic. And then you can go from the ground state to the excited state by shining a laser at it. But then because the level structure is so anharmonic, in principle or in practice, it's very unlikely that you would ever absorb a second photon. So it's a pretty kind of simple quantum system, but it's a kind of remarkable one because this is somehow like a kind of the ultimate nonlinear optical element. Right? So a single atom really sees one photon and two photons in completely different ways. So that's been known for a long time, but kind of what's special about one photon is it's non-classical. So in the past 10 or 20 years, atoms have become one of the preferred avenues for generating and manipulating non-classical states of light, in particular for quantum information processing. So that's kind of the dream. There's kind of one big problem with that dream, which is that single atoms and photons just don't like to talk to each other. One way to quantify that is you can imagine if I have a single atom, you can focus a laser beam onto that atom. So let's consider some beam that's focused to an area A. And you can ask, what's the probability that a single photon in that beam is going to interact with that atom and scatter off in another direction? And so it turns out the answer is just purely geometrical. So you can assign some kind of effective scattering cross-section to that atom. And that scattering probability is going to be nothing more than the resonant wavelength of that transition squared divided by the beam area. So on one hand, that's already a kind of remarkable result because this kind of effective size of the atom, the resonant wavelength squared, that's way bigger than the physical size of an atom, which is just kind of an angstrom. So it's by that fact alone that everything around us is not completely transparent. So that's good. But then it's not really good enough if you want to do quantum information processing because the diffraction limit makes it hard to focus a beam down to an area of lambda squared. So you can get a decent interaction probability if you really just try to focus a beam as well as you can, but not anything close to 100% interaction. So there's been some fixes or things that people have done for a very long time. So one trick is to not have a photon pass the atom once, but to have the photon hit the atom many times. So that's the field of cavity QED, where you've just put two very good mirrors around the atom. In that case, the probability of interaction is enhanced by the number of bounces that the mirrors can accommodate. And then if you're familiar with cavity QED or the James-Cummings language, you can rewrite that as this famous G squared over kappa gamma, or the cavity cooperativity factor. But again, this is nothing more than a kind of geometric argument. The other thing that you can do is instead of having one atom, have many atoms. So if one atom fails, another atom has a chance to succeed. In that case, the interaction probability is that of a single atom times the number of atoms. And then in a kind of atomic physics language, that quantity is known as the optical depth. So these quantities kind of seem quite fundamental, and it turns out they are. So it's widely believed that these figures of merit, cooperativity, or optical depth present kind of fundamental limits for anything you want to do with atoms and light in the end. So you can find a million examples of that. Here's a kind of experiment where they try to do some kind of quantum gate between a photon and an atom, basically entangle these 2 degrees of freedom. And somewhere in the paper says, well, in principle, it should work perfectly, except that the photon is not back reflected part of the time due to the finite cooperativity of the system. Okay, so cooperativity, or 1 over that, gives you the error. You can take a kind of similar system of atom in a cavity and create some kind of single photon transistor. Again, in principle, it should work perfectly, except you have a finite cooperativity, which gives you the error. And then you can, instead of having cavities, you consider atomic ensembles. Alexei has this really nice result. So if you want to take an atomic ensemble, you can try to create a quantum memory. So you send in a photon, and you try to get that photon to coherently convert into a spin excitation in the ensemble. And Alexei has this really nice result, basically saying no matter what you do, so you can have any strategy that you want, but once you optimize it, you get some kind of identical maximum efficiency, which only depends on the optical depth of the medium. Okay? And so these are 3 examples, but you can find 100 more. So it's viewed as a kind of pretty fundamental result in atomic physics, but then you can ask, is there some possible loophole to exploit? And here I'm going to focus particularly on the case of atomic ensembles. Okay, so the kind of naive figure of merit is it's the single atom interaction probability times the number of atoms. And you can ask maybe just a little bit more conceptually, why is the scaling this way? So this scaling kind of assumes something, which is it's a kind of per atom event. So each atom has a probability of talking to the good mode, in this case, a photon in this kind of Gaussian beam, versus bad modes, which is kind of scattering into all other directions, 4 pi, or free space. And then the effectiveness is just multiplied by the number of attempts that a photon has to interact with an atom. So it's multiplied up by the number of atoms. So that kind of seems reasonable, but there is an important assumption in there, which assumes that these atoms, when they fail, they're failing independently. So one atom has a chance to succeed. If it doesn't succeed, the next atom has a chance. And what that essentially assumes is that this kind of failure, this kind of emission into free space, or 4 pi, is independent. And we know that can't be true, right? Because atoms emit light as waves, and waves interfere with each other. So it's not that one atom is just kind of spitting out a photon into its own individual bath, but this bath is really shared by all the atoms together. So this is just kind of words right now, but if you're maybe familiar, a lot of you have probably heard of the physics of super and subradiance. And this is essentially what this talk is going to be about, using subradiance, so the idea that you can have an atomic excitation and really have that excitation be trapped in the atomic system, trying to use that kind of subradiance to enhance atom-light interactions. So I'll tell you more about subradiance later on. So basically the big question I hope to address in this talk is, can we suppress this emission into undesired channels into free space to enhance atom-light interfaces? So it turns out the answer is yes. And to try and convince you of that, there's basically 3 steps. So the first thing we need to do is we need to come up with some kind of formalism for atom-light interactions, which honestly accounts for this wave emission, which honestly accounts for subradiance. Because the typical model you write down for atom-light interactions, let's say in an atomic ensemble, just already assumes you have an independent bath built in. And so if you have that built in as your initial assumption, of course, you're going to get the normal optical depth limit out at the end. So I'll introduce that formalism. And the second thing I wanted to do is introduce subradiance. So subradiance, the idea has been around for a really long time, but I think one reason that people haven't really explored it in terms of enhancing atom-light interactions is, I think the origin is still pretty mysterious to people. And it certainly was to me. But then there's one kind of simple case you can consider, which is if you take an ordered array of atoms in free space, it turns out that subradiance is nothing more than guided modes of that atomic array. So these atoms are nothing more than a fancy optical fiber, and that's where subradiance comes from. So the third thing is, it turns out subradiance doesn't really help you to enhance atom-light interactions. So subradiance means you have some excitation in your atoms, and it just stays there forever. So it's just really decoupled from light. And if you want an efficient atom-light interface, what you really want is that you want those atoms to talk very well to a mode that you desire, let's say a Gaussian mode, and it's simply suppressed into all other directions. So I'm going to introduce another concept called selective subradiance, which exactly gives you that. And you can get this selective subradiance by, it turns out, trapping atoms close to an optical nanofiber or some other kind of photonic structure. So I'm going to kind of try to keep it conceptual and simple for most of the talk. And then at the end, I'll try to say a little bit about experimental considerations. What would it really take to see these effects? So the first thing is developing a formalism. And the workhorse for this formalism is going to be the classical electromagnetic Green's function. So here's the kind of formal definition of the Green's function. What you see is it's nothing more than the solution to the electromagnetic wave equation in the frequency domain, given some kind of delta function source. So what it physically describes is, well, imagine I have some kind of oscillating dipole. So in free space, I know how the oscillating dipole radiates. And I'm allowed to have some kind of dielectric materials nearby, some permittivity epsilon. And this Green's function simply says is going to tell me what's the total field at a point r, given a source at r prime. And the total field, of course, can not only consist of the free field emitted by this dipole, but all the rescattering by any kind of nearby dielectric structures. So that's what the Green's function just physically describes. Technically, it's a tensor quantity. So these indices alpha and beta can take 3 values, x, y, and z. And that's simply because your source dipole you can orient in 3 directions. And then the electric field at this point r has 3 directions as well. So it's a tensor quantity, but for the purposes of this talk, we'll ignore that kind of tensor nature. And again, the simplest case is just free space. So in free space, this Green's function is nothing more than the free space dipole radiation pattern. Okay. So this is a formula that you can just look up in any electromagnetics textbook. So what we're interested in the end is how, when you send in a kind of pulse of light, how it interacts with atoms. And we're going to do something kind of strange here. So we're interested in how light interacts with atoms and propagates. And the first thing we're going to do is we're going to throw the light away, okay, as a degree of freedom. So that kind of sounds strange, but it actually turns out to be very helpful because especially when you're talking about the quantum regime, when you're talking about a propagating field, it's a continuum, right? So even one photon already has an infinite Hilbert space associated with it because it can live anywhere in space and or have any frequency. Okay? So let's get rid of that infinite Hilbert space. And to see that you can do that, well, you can actually just make a kind of classical analogy. Imagine I have some kind of input field, let's say a Gaussian beam, which I assume that I know. And it's going to be interacting with some kind of point dipoles. And I'm going to assume that I know the properties of these point dipoles. In particular, I know their polarizability. So once I know the field at that location, I know the induced dipole moment. And then what I essentially want to be able to calculate is the field at any other point in space. And again, because I know the radiation pattern for a dipole, I can just formally write down the total fields. The total field in the frequency domain is going to be what I send in, plus that which is rescattered by the dipoles. So the rescattering is just going to be proportional to the dipole amplitude itself, times the Green's function, which is what propagates that dipole out to my detection point, r. So this is certainly kind of true classically and quite intuitive, but the point is classical and quantum fields, they both propagate the same way. They both obey Maxwell's equations. So this quantity, this equation is true if I put operator hats on all the fields and all the dipoles as well. Okay? So that's, again, formally true. It's still not easy to use yet because this is true in the frequency domain. But then if I try to use it in the time domain, this kind of product of quantities becomes a convolution in the time domain. And here's where the kind of trick comes in, where having atoms really makes life simple. So an atom is a very high Q resonator, right? So it has an optical resonance frequency of hundreds of terahertz, but usually a kind of spontaneous emission line width of a few megahertz. What that means is within a few megahertz, the dipole moment has a huge dispersion, right? But then within a few megahertz, in kind of typical dielectric settings, the Green's function is not changing very much. So what you can do is instead of treating the Green's function as a function of frequency, you can just evaluate it as some central frequency, let's say the resonance frequency of the atoms. And now that time convolution disappears. So now I got a kind of instantaneous equation in time, an input-output equation for the atoms. So what I've done here is I've simply just rewritten this kind of quantum dipole in terms of the atomic coherence of a two-level atom and times some atomic physics quantities like the single atom spontaneous emission rate and the atomic dipole moment. So this equation is quite nice because what it really says is even though in principle your field is a continuum, it doesn't have an infinite number of degrees of freedom associated with it. All the real degrees of freedom are simply encoded in the atoms themselves. So what about the atoms? So we know the atoms interact with the fields. We can write down some kind of Heisenberg equation that expresses that. But then the fields are not independent. So the fields just depend on the atoms themselves. And so these equations that you write down for the atoms, in the end, they're only going to evolve atomic degrees of freedom. So from that set of equations, I can back out some kind of effective Hamiltonian that describes how atoms interact with each other as they exchange light, but only, again, involves atomic degrees of freedom. So this is going to look like a kind of quantum spin Hamiltonian. So again, there's some kind of atomic physics constants which aren't so important. The main thing is this kind of spin term here. So what it physically describes, I think, is quite reasonable. What this term describes is one atom, which is, let's say, atom J, can start up in the excited state. It can drop down to the ground state. And then another atom I, which is in the ground state, can hop up to the excited state. So of course, that's what a kind of photon-mediated interaction should do, right? It should just facilitate atomic emission and reabsorption. And then the kind of strength of that, again, is just going to be proportional to the Green's function, the electromagnetic Green's function, which tells you how light propagates, how electromagnetic field propagates from atom J to atom I. So just to be a little bit formal here, this effective Hamiltonian is not strictly legal. Okay? So this Green's function is not real, it's complex. And so this is actually a non-Hermitian Hamiltonian. What that means is if I really want a kind of proper quantum description of the system, I have to tell you what the quantum jump operators are associated with this non-Hermitian Hamiltonian, or I have to write down some kind of longer master equation or density matrix equation to describe the full evolution. So technically that's true. It's not going to be very important here, which is why I'm just going to restrict it to this kind of shorthand notation. But the fact that it's non-Hermitian does encode important physics, because it not only describes this possibility of coherent interactions, where atoms exchange their excitations back and forth, but it also describes spontaneous emission, and particularly allows the spontaneous emission to be collective as well. So just to see that this kind of effective Hamiltonian is reasonable, we can see what happens if we have just a single atom in free space, right? So we all know what a single atom in free space does. You bring it up to the excited state, and just spontaneously emits at a rate gamma naught. So here's my effective Hamiltonian for any number of atoms. And then if I have a single atom, so I has to equal J. If I go from the excited state to the ground state, and then from the ground state back to the excited state, that product of lowering and raising operators is nothing more than excited state population. Okay, so this is the Hamiltonian now for a single atom. And then to calculate the Green's function, well, you just have to look up what's the dipole fields created by oscillating dipole in free space at its own location. So in that case, what you find is this I times the frequency divided by 6 times pi times c. And then when you simplify all of that, you indeed get that the effective Hamiltonian is anti-Hermitian, which describes spontaneous emission. And then the spontaneous emission rate, gamma naught, is exactly what you would predict. Okay, so this Hamiltonian encodes normal things like single atom spontaneous emission. Okay, so here's just the spin model again. I should say a little bit about, there are some limits where this spin model breaks down. So the first is, I did assume that this Green's function, the electromagnetic Green's function, is not changing a lot over the kind of atomic resonance bandwidth. Okay? So of course, if you have dielectric structures, which themselves are very high Q, that can break down. So one kind of easy example to see is if you have cavity QED, but in the strong coupling regime, you can get vacuum-Rabi oscillations. Okay, that's not going to be captured by this spin model. Another case where this kind of dispersion of the Green's function becomes important is just if you have very large systems. Okay, so this kind of spin model ignores time retardation. So one atom sees another atom instantaneously. But if you have a single atom and you have it in an excited state, when it spontaneously emits a photon, typically that photon is about 10 meters. So for this kind of Hamiltonian here to be valid, at least in free space, it means your next atom or all the other atoms have to be within 10 meters of one another. Okay? So don't build BECs the size of this room, and then you can use this equation. So one nice thing about this equation is really it's completely general. So aside from these kind of limits, it really captures any system of atoms interacting with light, and it treats them on equal footing. So you could use these equations to describe cavity QED, free space atomic ensembles, atoms near nanophotonic systems, et cetera. And that's what we're going to exploit later on. So let's apply these equations to one simple system, which is a chain of atoms in free space.
So if we ignore this time retardation, and I just do this and take the imaginary part and then build the jump operator based on this, then I get the correct answer, as long as I do the time, ignore the time retardation.
Yes. Yeah. Oh, so for one atom, it's always.
Yeah. No, but for multiple ones, when you have some.
Yeah, that's right.
When the distance C over L is comparable to gamma.
Yeah, so in that case, you would generally not be able to use the spin model. You would have to keep the field as a real degree of freedom.
Okay, so since we're asking questions, I'm confused by this.
Okay.
Because normally when I hear the word retardation, I'm thinking distances that are large compared to a wavelength, or at least comparable to a wavelength. And here you're saying distances that are comparable to a decay time.
Yes.
So could you say a little bit more about that?
Yeah, so honestly, that's something that,
there are retardation effects due to the phases.
Right.
And you're taking those into account.
Yes. Yeah, so honestly, that's something that really confused me for a long time as well. So, there's all these historic papers on Born-Markov approximation and what it means to be Markovian. right? And a lot of times what people say is indeed that this system should be smaller than a wavelength. So it just turns out that that's not true. I mean, and it's very abstract. So I guess
take account of the retardation terms.
So
do the phase, right?
Yeah. So that's the thing. So propagation phase is included in this Green's function, and so yeah, in that spirit, if you leave out that phase, then it's certainly true that atoms have to be very close together. But yeah, I think the surprise to me certainly was that this Markovian approximation is valid for scales that are much longer than I naively thought before, what I think most people would believe. And then to really check that that's true, what you can do is, in some cases, you can just solve it exactly, including retardation. And you really see that the kind of expansion parameter is this kind of length of a photon that's emitted. OK, so here's the kind of spin model in general. And what I want to do now is just apply it to atoms in free space. So again, the Green's function in free space is just the kind of dipole emission pattern, which you can look up in any book. So we still have to specify a geometry. And so to be specific, I'm going to take a finite number of atoms, so n atoms in a row, with a well-defined lattice constant d. So it's a 1D chain of atoms, but they live in 3D. Okay, so the Green's function here is the 3D electromagnetic Green's function. So the first thing I want to do is just consider one excitation among these n atoms. Okay, in that case, the Hilbert space is pretty small. So either the first atom is excited, the second one, third one, or so on. So there's n possible states. And then within this subspace of one excitation, this Hamiltonian is just an n by n matrix. So I can easily diagonalize it. So you can do that just numerically. And in general, you get n eigenstates. And each eigenstate is going to be some superposition of excitations sitting on different atoms. Okay, so it's very unlikely that when you diagonalize this Hamiltonian, one of the eigenstates is just a product state of one atom being excited. Okay, so generally, these eigenstates are superpositions of atoms being excited. And then the corresponding eigenvalues, they're going to be complex because the Hamiltonian is non-Hermitian. So there's going to be a real term which describes a kind of real energy shift. And there's going to be some imaginary term which describes the decay rate of that collective excitation. And in general, these quantities, the energy shift and decay rate, they're going to be different than the bare single atom values. So the energy of these eigenvalues is not going to be the single atom resonance. The decay rate of these collective states is not going to necessarily be the single atom emission rate due to this process of photon exchange. So let's just kind of see what the numerics tells us. So this plot is a little bit complicated, so let me try to explain it slowly. So I'm going to take just a fixed number of atoms here, 30 atoms in a row. And I'm going to consider just, for example, some fixed lattice constant. So for example, on this vertical line, this is the lattice constant that's about 2.1 times the free space, or sorry, times the resonant wavelength. So I have 30 atoms, which means I have 30 eigenvalues. And so on this vertical cut, you can't really see it, but there's actually 30 distinct points, which tells you the 30 kind of resonant energies associated with each eigenstate. And what you see is that when the atoms are this far apart, about 2 wavelengths, everything is pretty close to 0. Okay, so these energy shifts, in principle, they exist, but it's a very small fraction of the free space single atom emission rate. You can do the same thing not for the frequency shift, but for the decay rate. And again, what you find is, in principle, you have 30 different decay rates, but then they're all very close to the single atom decay rate. Okay. And then what you can do is, now I'm going to sweep the lattice constant. So look at smaller and smaller lattices. So as these atoms get closer, you see that these the kind of changes in the frequency shifts and the renormalization of the decay rates, they become more and more prominent. So by the time you're at 1 wavelength, you get kind of a 50% renormalization of some of these decay rates. You can get closer to lambda over 2. And then when you take a peak before lambda over 2, the floor just falls out from beneath you. Okay? So you have states where the decay rate really goes to almost 0. Okay, so these are subradiant states. There's one excitation shared among these atoms, but it takes them forever to decay out into free space. So you can ask how close to 0 is it. You can take the same plot, and you can plot it on a logarithmic scale. And what you can find if you go and analyze it more carefully is if you just look at the few darkest, or the few most subradiant states, the lowest decay rate goes like 1 over the number of atoms cubed. And then the second most subradiant state goes like 4 times that, 9 times that, et cetera. Okay?
So if we average over all of those, what's the mean decay rate of all states?
I think it's actually still quite subradiant, but I think average, so let me try to ask the experimental version of that question, which I guess what you're interested in. So when you experimentally measure, the thing is you come in with you excite the atom somehow with a beam from free space. And so what happens is that beam does not excite these modes evenly. So what you tend to excite, which maybe is kind of intuitive, is you tend to excite the more subradiant ones because those are the ones that talk to light in the first place.
So I'm not sure what the question is. I understood the question, yeah. If I average across all of them,
Yes.
I get the average atomic rate, right? All 30 states.
So if I just take an average,
Ones and subradiant ones.
yeah, so it turns out in 1D, the super radiant ones are not very super radiant. They only decay, yeah. But then you have all these decay rates that are basically 0. So when you average on it, you can get a rate that's still quite subradiant in the end. But so that's true mathematically. But then what I'm saying physically is, when you do an experiment, you come in with some kind of probe beam which doesn't necessarily excite or talk to all these modes in the same proportion. Okay.
Yeah. You said that the superradiant states are not very superradiant, but I would think that when the spacing gets quite small, that those superradiant states would become rather super.
Oh yeah, I'm
like
sorry.
N
Yeah.
times faster than there would be one
Yes.
state that would be n times faster.
Yeah,
And
I'm
when
sorry.
they're very
Yeah.
close.
Yeah, so that also depends on the dimensionality of the system. So here I'm considering a 1D chain.
Right, but in a 3D world.
Yes. So if I, for example, consider like a 2D membrane or a 3D lattice, then I would have states where the emission rate increases with the number of atoms.
Okay, but I'm not, even in 1D, if they were all much less than lambda bar, what
Okay.
difference does it make that they're arrayed in 1D? Wouldn't they still be superradiant?
Oh, okay. So maybe there is an order of limits. So I can take some finite n and just put them so close together that I get the decay.
Yeah, which is less than lambda
right.
bars.
Yeah.
Something.
But then if I kind of take the limit of large n first, so if I assume I have a system which is bigger than the wavelength, then in 1D I don't get any increase with n. Okay, so what this plot shows is that this kind of interference of wave emission really matters when atoms are at close distances, smaller than lambda over 2. So let's try to understand why that happens. And to understand why, let's consider a different limit, which is just an infinite lattice, okay, but still one excitation. In that case, because I have this discrete translational symmetry, I know that all my single excitation eigenstates are going to be block modes. Okay? So an eigenstate is going to be some superposition of atom J being excited with a relative phase of e to the I kz. So what I can do is I can diagonalize the Hamiltonian given these block modes. And I can represent the spectrum by a block band structure. So let me just draw out a kind of empty, just the axes first. So again, this Hamiltonian is complex. So there's going to be a real part of the energy and an imaginary part. Let me just plot the real part for now. So first, the dispersion relation, the block band structure is going to live within the first Brillouin zone. Right? So k is going to be this block wave vector. And its distinct values go from minus pi over d to plus pi over d. There's going to be one important scale in here, which is the atomic resonance frequency. So I just kind of denoted that in red. So this is the single atom bare resonance. So I haven't diagonalized anything for you explicitly, or I haven't shown you any equations. But what you can imagine quite generically is, an atom, again, is a very high Q element. It only talks to light within a very narrow frequency window. So regardless of what the exact shape of the band structure is, you can kind of say with decent confidence that band is going to be very narrowly centered around the bare atomic frequency. And then its width is going to be on the order of the single atom free space emission rate. So actually, what you see here is actually completely blown out of scale already. Omega Eg, again, is kind of 300 terahertz. And then this gamma naught is a few megahertz, which is be completely flat. Okay? So you basically have a very flat band for these atomic states. There's a second set of lines which is important to draw in, which is the free space dispersion relation of light, omega equals ck. To understand why that's important, well, so far I'm just talking about the atomic spins, but remember that it is a kind of field, these spins are coupled to the fields, and in principle I can reconstruct that electric field. And because I have these kind of block structure, of course, the electric field has to have the same wave vector as well. So this block mode k of the atoms creates an electric field which has the same k vector along the direction of the atomic chain. Okay? At the same time, it's allowed to have some kind of transverse structure. So let me just take a kind of plane wave decomposition of that. So I'm allowed to have some kind of structure for the electromagnetic field transverse to the chain with some perpendicular k vector k perp. Okay? And because I have electromagnetic field, it has to satisfy Maxwell's equations. In other words, the dispersion relation has to be that k squared, the k vector in the direction of propagation, plus k perpendicular squared equals omega over c squared. And so what you see is that this line of omega equals ck separates two very different electromagnetic field solutions. In particular, if k itself is bigger than omega over c, that implies that k perpendicular has to be imaginary. In other words, the electric field has to be evanescent or guided in the transverse direction. So on this kind of plot here, what it means is I have this dispersion relation, but then the part of the dispersion relation that lives in this triangle, its decay rate really has to be 0. Right? Because the electromagnetic field associated with this atomic excitation is decaying evanescently out to infinity. It can't radiate energy away. And then the states within this triangle, within this so-called light cone, they're going to be radiative. Okay? So they're allowed to radiate energy out to infinity and to decay energy. So what does that say? Well, an infinite chain really can support states with exactly 0 decay rate. And these states are nothing more than guided modes of this atomic chain. This atomic chain is nothing more than a kind of fancy optical fiber. Okay? So an optical fiber guides light in exactly the same way. It has a k vector which is beyond that of the free space dispersion relation. So the only condition for that to happen, again, assuming that this band is relatively flat, is that the atomic resonance frequency has to intersect the edge of the Brillouin zone below where the free space dispersion relation intersects. Okay, so you can rewrite that in terms of distances if you want. And in terms of distances, that's exactly the condition we found before for finite systems. When the lattice constant is below lambda over 2, then you're guaranteed to have these kind of guided, perfectly guided modes that never decay. So again, this is kind of the infinite system. And then you can go back and reinterpret the finite system if you want. Well, so I know an infinite system now of atoms is just a fancy optical fiber. And if I cut an optical fiber, it's allowed to decay just by firing light off the ends. And we can check that numerically. So we have the ability, given these spins, to reconstruct the electromagnetic fields. So you can take this kind of set of 30 atoms, look at the most subradiant state, and look at the light intensity that's being emitted. And indeed, you see it's just launching light off the end like a normal optical fiber would.
If it's like a fiber, then it only should depend on the end, not the length of the fiber.
Okay, so it's a fancy fiber because it's very poorly impedance matched at the end. So the end actually forms a kind of decent finesse cavity. So it is like a fiber, but the light actually, when it hits the end, it actually reflects with a pretty high probability. And that's why the 1 over n cubed, you get the 1 over n cubed scaling instead of 1 over n. Yeah. So far I was talking about a single excitation shared among these atoms. And at least at the level of calculation here, this single excitation physics is completely classical. So I don't need atoms or spins to see this physics. If I have just point dipoles, I would also see the kind of same types of excitations. But one of the kind of interesting about atoms is that we would really like to do quantum things in the end. So it would be nice if we could store many excitations in the atoms and still have them be subradiant. So that's a kind of interesting question to ask. Can you encode many excitations in subradiant states? So let me just kind of illustrate a toy example to illustrate why this problem is quite subtle. So let's go back to the single excitation manifolds. I argued before that if I take the most subradiant excitation, it has a decay rate that goes like 1 over number of atoms cubed. So I can take that, it's going to be some superposition of atoms being excited with some amplitudes Cj. In general, I would just solve it numerically, right, by diagonalizing my Hamiltonian. But the point is there's some collective spin operator, excitation operator, that you can associate with this superposition of atomic excited states. And now I can ask, well, what if I create 2 excitations? And the natural thing to maybe try first is, well, what if I just take that single excitation and try to create a second one exactly on top? Is it going to be an eigenstate, and is it going to be subradiant? So if it was not a spin, if it was boson, the answer would certainly be yes. You have a quadratic Hamiltonian, and the decay rate for 2 excitations would just be twice that of a single one. But because we have spins, the answer is no, and it turns out it's not just a little bit no, it's very much no. So to try and see that, let's just plot out what the kind of 2 excitation wave function looks like. So I take the single excitation state, I square it, and I can write it as a pair, a sum of any 2 atoms, I and j, being excited. And Cij is just going to be the amplitude of that wave function. So I can plot out Cij on a kind of 2-dimensional space. And what you see is that it's relatively smooth overall, except along the diagonal, this amplitude is 0, right? Because I can't take the same spin and excite it twice. And the problem with that is I argued before that this origin of subradiance is that you have k vectors that sit beyond the light line. Okay? And anytime I have a wave function with a sharp kind of cut in it, this is kind of like a discrete delta function. When I Fourier transform it, it has wave vectors everywhere in space. So this kind of 2 excitation wave function actually leaks strongly back into the light cone. So first of all, it's not an eigenstate, but you can calculate what the kind of expectation value is for the decay rate. And you indeed see that most of the subradiance is lost. It's not 1 over n cubed anymore. It actually increases to being 1 over n. So that brings up the question, how do you construct many excitation subradiant states? So again, let's start with my single particle eigenstates. M is going to be index of how subradiant they are. So m equals 1, it's the most subradiant. M equals 2, the second most, and so on. And I have some wave function amplitudes that I know for the single particle states. And then just from intuition, we know that if I want a state to be subradiant, the wave vectors should sit beyond the light line. So the most subradiant single particle eigenstates already give you that. But I really want these excitations to also be spatially non-overlapping. Right? That's what prevents these kind of kinks in the wave function, which have all these wave vector components. And maybe one piece of intuition is, well, if you take these two and put it together, that kind of tells you, well, I should create a kind of Fermionized wave function. Let's try to build Pauli exclusion into the many-body eigenstates. So then they're guaranteed to just be physically or spatially separated. So let me give you an example for 2 excitations. So again, for 2 excitations, I have this 2 excitation amplitude Cij. And if I want to create the darkest or most subradiant 2 excitation state, I would write the Cij. I would try to write it in terms of the 2 lowest, the 2 most subradiant eigenstates of the single particles. Okay? But I would write it in some kind of anti-symmetrized way, which guarantees that these 2 excitations sit as far away from each other as possible. So here's what that kind of 2 excitation wave function looks like. You indeed see that you have this kind of 0 down the middle, but it's a kind of smooth 0. Okay? It's not a sharp cut in the wave function. And then when you calculate the decay rate of the state, you again see that it's just going to be the sum of the single particle decay rates. And so you preserve this kind of 1 over n cubed scaling. Okay, so it is possible to have several excitations and have them be subradiant. They just can't touch each other. So you can extend this argument to the many-body limit. So if I have n atoms and m excitations, the strategy is to take the m lowest single particle states and construct some kind of Fermionized wave function out of that. And then by this argument, the decay rate of that state would be just the sum of j squared over n cubed. So it would basically be proportional to the density of excitations cubed. Okay? So that's a kind of nice final result. In the thermodynamic limit, you can have many excitations and still have the system be dark. What's important is to just have a low density of excitations which don't physically touch each other. And I think this gets a little bit to the question that you asked. How do you couple to these subradiant states from free space? So there's a kind of first order answer you can give. You can kind of try to play funny tricks, but the lowest answer is it's hard, right? And the reason it's hard is, if you have this chain of atoms in free space, the most natural thing to do is just come with a free space laser and hit it. But then this free space laser lives in this part of the light cone here because it's a radiative mode, right? It propagates energy out to infinity. And you see that there's just a kind of natural impedance mismatch between talking to these subradiant states, coming in with some kind of free space laser. So again, you can try to figure out clever tricks to get around that. But maybe the most kind of natural thing to think about, given this diagram here, is, well, let's not try to excite these modes from free space. Let's try to excite it from another set of guided modes, in particular from some optical nanofiber that we slide underneath this chain of atoms. So let me maybe give 2 or 3 slides about just current experiments where people can interface atoms with nanofibers. So the way a nanofiber works is it guides light by total internal reflection. You have a high refractive index core surrounded by a lower index cladding, which in this case is going to be vacuum. So that's kind of the ray optics picture of an optical fiber. But the real picture is, it's not that the field only lives in the core and not in the cladding at all. The field actually extends into the cladding, but just evanescently decays away. And it turns out when your fiber is really thin, so when the fiber radius is much smaller than the optical wavelength, that kind of evanescent field into the cladding can actually extend out quite a distance. So here's a kind of just numerical plot of that. Here's a 250 nanometer radius fiber. And what I'm plotting here is the field profile. And you indeed see that there's a lot of field that lives in the vacuum region, but in a kind of evanescent fashion. So what that means is, you can use that to try and both trap atoms near the fiber and to have atoms interface with guided modes of the fiber. So here's a kind of experiment, pioneer experiment from Arno Rauschenbeutel's group. Here's just a schematic of it. You start with a normal glass fiber. You pull it under a flame until it becomes very thin. And then you can run counter-propagating guided modes through the fiber to create a 1D lattice. So it's a perfect 1D lattice. There's a question of how you fill these sites. In practice, you have a kind of magneto-optical trap flying around, and then these kind of sites are just filled probabilistically. Okay? So you trap atoms with light that's just completely off the resonance frequency of the atoms. But once the atoms are trapped there, the atoms can interface pretty efficiently with near-resonant photons that are guided through the structure. So imagine that you just have one atom that's trapped, never mind how. And what you can do is you can bring the atom up to the excited state and ask, with what efficiency does that atom emit a photon into the fiber versus into free space? So the rate that emits a photon into free space is more or less the vacuum emission rate. It's modified a little bit by the dielectric, but not by very much. And then you can emit into the guided modes in realistic fibers with about 10% efficiency. I guess the point now is, now that we slide a kind of optical fiber underneath, the optical fiber has a set of guided modes, which also lives beyond the light cone. And so those guided modes of the fiber should be able to talk perfectly to these subradiant states of the atomic chain. Okay, so here's a kind of illustration of that. The blue curve was the atomic guided band in free space. And then the red is a kind of schematic of the fiber guided mode. And they intersect each other perfectly, so they can start to hybridize. So one thing I should say is, I started by talking about subradiance, but of course this is not subradiance anymore, right? Because the atoms will perfectly emit light into the fiber. So it's not subradiance, it's what I'll call selective subradiance. But my claim is that's perfect, okay? That's exactly what you want. Because remember, if the game is to enhance atom-light interfaces, what you really want in the end of the day is you want your atoms to talk very well to your preferred mode of interest, in this case the guided mode, but just be completely suppressed from talking to all other modes, in this case, to free space. Okay? So it's not subradiant, it's selective subradiance. Talks perfectly well to the fiber, but not at all to free space, at least, ideally. So we're going to see if this kind of configuration can beat these so-called optical depth limits of atomic ensembles. So we have to set up a kind of counter example or a counter model to that. So what's the typical thing that people assume about fibers? Well, if you have fibers, a fiber and many atoms coupled to it, people usually assume that you have a collective emission or enhancement into the guided modes. So you have n atoms. Those n atoms can emit with a rate that's n times bigger than that of a single atom. But again, the typical assumption is that this emission into free space is independent. Okay, so it's a single quantity. It doesn't depend on how many atoms you have or their spatial configuration. And then what we want to contrast that with is a collective emission model where you really account for this wave emission honestly. And the way we do that is, again, to exploit this kind of spin model. Okay, so we have this effective Hamiltonian that describes how atoms interact by exchanging photons. You have to calculate the Green's function, which you can do for a cylindrical nanofiber. It's an exactly solvable system. It's not nice, but it's possible. And then you have this kind of field propagation problem, which says your total field is what you send in, plus that which is rescattered by the atoms. And again, a cylindrical nanofiber, you can solve the mode exactly. So you can just project this field equation into the guided mode of the fiber. So that's what we kind of do on a heuristic level. So let's talk about one specific example, which is that of photon storage. Okay? So imagine I come in with a guided photon and a bunch of atoms which are initially in the ground state. And I want to ask, what's the probability or fidelity with which I can absorb that photon and create some kind of collective superposition of an atom being in the excited state. Okay. So that's the photon storage problem or quantum memory problem. It's actually a little bit easier, at least for these purposes, to study the reverse of that. Okay? And the reverse process has to be identical by time reversal symmetry. So instead of studying the storage problem, what I'm going to consider is if I have a collective excitation of one atom being in an excited state, what's the fidelity with which it'll emit a guided photon into the fiber versus free space. So in principle, you can do the calculation for 2-level atoms. I'm going to jump to 3-level atoms for a reason you'll see in a couple of slides. So with 3-level atoms, the story kind of works as before. So you have a ground state G and excited state E. You assume that the E to G transition can emit photons into the waveguide as well as into free space. And then I'm going to have this excited state E also be coupled to an extra ground state S, which is, let's say, metastable. Okay? And it's going to be coupled through some kind of external classical laser field with a Rabi frequency that I can tune. And so it doesn't really change the physics at all. So for example, you could start with one atom. So I have n atoms, three-level atoms. I start with the system in a superposition of one atom being in the state S, but I don't know which one. I turn on the pump field, and that S state will leak into the excited state and then leak into a photon into the waveguide or leak a photon into free space. And whether you have 2-level atoms or 3-level atoms, within the independent emission model, the error of that process is going to be gamma prime, the single atom emission rate into free space, divided by the collective emission into the fiber. So gamma prime over n times gamma 1d. And that essentially defines the optical depth for this nanofiber system. So that's the limit that I'm trying to beat. So now I have this kind of collective emission model. I have this Hamiltonian, including the Green's function of the fiber, which I'm just going to, again, diagonalize numerically. And I'm going to look for the eigenstate with the highest emission probability into the waveguide. So what I'm plotting here is the error of that process versus number of atoms. So in the independent emission model, I can release a photon with an error of 1 over n. But once I account for this collective emission, I can get an extra factor of n. So now my total error is 1 over n squared. So this 1 over n squared, you can ask where does it come from. In particular, it doesn't seem that ideal because we already get a factor of 1 over n just from normal collective enhancement of emission into the fiber. But we only gain an extra factor of 1 over n of suppression of emission into free space. But we already saw earlier, if I just have a chain of atoms in free space by themselves, I can suppress emission like 1 over n cubed. So where are those extra factors of n going? So here's a kind of diagram which will explain it, and I think which will make all the experimentalists who work with optics happy. So if I have a fiber, so I have a normal fiber, that guides light totally fine. When I have this part of the fiber with a regular array of atoms, that guides light totally fine. So I have two perfect fibers, but they're different. And when I connect them together, in general, I have a lot of scattering losses, right? Because the modes are not spatially matched to one another. So that all the extra factors of n are just going to the scattering losses at the interface. Okay? So what do I need to do? Well, I need to go to Mohammed's lab, and I need to steal a connector from him. Right? So we need to impedance match these two fibers together. Well, how do you do that? Well, one thing you can do is you can take advantage of this kind of 3-level structure and this external pump field. So I can try to now spatially tailor this external pump field so that the atoms at the very ends only gradually start to couple to the fiber. Okay? So it's like the atoms at the end barely couple to the fiber, and then this coupling gets adiabatically stronger and stronger as you enter the middle. So it's kind of like an adiabatic mode matching. And so you can do that calculation. So again, it's this process of photon generation or storage. And now what you find is that the error versus number of atoms goes exponential. Okay? So it's not 1 over n, it's e to the minus n. And then just for this kind of physical nanofiber system, within the collective emission model, the error was about kind of 10%. And then if you do this process here, the error has dropped to 10 to the minus 13. Okay, so you're just limited by other factors rather than subradiance. Okay, so maybe I'll take a couple minutes to talk about what you might do to see it experimentally. So I'm not going to lie. The experiments are going to be really hard. And there's some things we don't understand yet. So the first thing is, it's pretty hard to create a 1D chain of atoms with a lattice constant that's smaller than lambda over 2. Turns out if you create a 2D array, you can extend the range of the subradiance a little bit further. So the lattice constant now would be lambda over square root of 2. But you would also need one atom per site. Okay, that's what gives you a kind of ordered system, and that's what allows this kind of photonic band structure to take over. So what could you imagine doing? Well, maybe this kind of quantum gas microscope would work. You prepare, for example, a 2D optical lattice in a Mott insulating state. And at least in some region, you have exactly this kind of configuration here. If you want to do this kind of selective subradiance and nanophotonic systems, well, in that case, it turns out the lattice constant is pretty easy to realize. You can just create nanophotonic systems where the lattice constant of that structure itself is below lambda over 2 of free space. And then the challenge there is really, well, you can make these structures in lab. You can have a trap. You can have many trapping sites. But then it's still very hard to fill these sites with atoms. Okay? So that's the kind of big unknown. There are possibilities. For example, in free space, it's been demonstrated that you can have optical tweezer arrays that you can program. So you can have 50 atoms in a row in free space, each in their little optical tweezer. And then maybe you can imagine combining that kind of technology with these nanophotonic systems. So it's hard, but maybe it's possible. So there's another big issue, which is hyperfine structure. So far, I was talking about atoms assuming essentially a single ground state. Okay, so it can be a 2-level atom with one excited state, or it could even be an isotropic atom. In that case, this kind of subradiance is always there. Okay? And the reason is because there's always an interference channel between emission and reabsorption. So if I have a single ground state, if one atom goes up to the excited state and it re-emits a photon, there's another atom back in the ground state to pick up that photon. So there's always that interference that can occur. But then when I have multiple ground states, that interference doesn't necessarily exist anymore. So for example, if I have 3 ground states and I optically pump my atoms to one ground state in the beginning, if one atom now hops up to the excited state E, it can emit a photon, well, back down into the same excited state, which again gives you an interference channel. But it could also emit into some other ground state where there's no initial population. So it's impossible to have subradiance or interference on that channel. Okay. So there's a few possible fixes for that. You can try to employ a cycling transition, so that really makes your atom look kind of 2-level, as close as possible. That only works, unfortunately, for 1D chains, because even when you start on a cycling transition, when an atom emits a photon, you have to guarantee that emitted photon still looks sigma plus to the next atom that's trying to pick it up. Okay, so that works in 1D, but if you have atoms in all different directions, the polarization gets completely scrambled. So one possibility is maybe instead of using your normal alkali atoms, you can find fancier atoms without hyperfine structure, like strontium atoms. There's also a kind of related issue of, I was talking about 3-level systems, but again, that has the same problem of where did this extra ground state level come from. So as far as I know, the only way to do a kind of 3-level system at the moment is to exploit some kind of metastable higher lying level, which just has a very low decay rate. So there's a lot of kind of issues that need to be sorted out. Honestly, I don't know, what you would do in a lab right now, but I think it's a question that's worth exploring. So with that, I'm done. So just to kind of conclude, I think to me it's really fascinating that we all know that spontaneous emission is kind of like a barrier to everything you want to do in atom-light interactions. But what if you could just shut it off, right? So what's the real kind of new ceiling if you can really exploit subradiance to your advantage? So we know the answer already in one case. For photon storage, you can do exponentially better than before. But this kind of spontaneous emission dictates almost everything in atomic physics. So if you want to do nonlinear optics, photon gates, do spin physics, you want to build lattice clocks, spontaneous emission really enters in as fundamental limits. And I think it'd be really fascinating in the future to find out what the new ceiling is, if you exploit subradiance. So with that, thanks for your time.